All right. In this section, we're going to start to take a look at the process of evaluating triple integrals using a new type of coordinate system, using cylindrical coordinates. Okay, now this can seem at first glance to be like a very weird or unnecessary overcomplication, but it's most certainly not. You might recall that when we worked with double integrals, we sometimes found it easier to treat kind of our base region of D as a polar region, because maybe it was like a circle or something bounded by some sort of like a polar function. Well, when we deal with cylindrical coordinates, we're going to see that we have almost the same sort of a thing. When we deal with cylindrical coordinates, we're going to be navigating out into a point in 3 space and saying that that particular point is going to have 3 components, or sorry, 3 coordinates. It's going to have an R value dictated by being down here, how far I have to walk from the origin to get under the point, how far did I have to rotate off the x-axis in order to get to that spot, and then my z is kind of just my regular old rectangular coordinate. What you can kind of imagine, though, is that if you could imagine wrapping your hand around that particular z vertical line and pulling it in a big circle, you would create the shape of, you guessed it, a cylinder. So these are typically referred to as cylindrical coordinates. You kind of first imagine where exactly it is that you want to aim in the xy plane, so you can walk to be either under or, I guess, above your point, if your point had a negative z. And then you would just walk up or down, just perfectly straight up or down, to get to your associated point. So this is the process of cylindrical coordinates. And we're going to go ahead and be able to kind of summarize how we can do certain kinds of conversions then in this particular case. So here's one thing that's super, super easy to see. If I wanted to find x in base of the polar coordinates, cylindrical coordinates of a point, I could really just use the polar coordinates. I already know from polar that x is equal to r cosine theta. And you'll see that down here in the xy plane, I kind of have that same sort of triangle still shaping up. Nothing's changed about the x coordinate. The y coordinate also hasn't changed. That's still r times the sine of theta. The only thing that has potentially changed is now we have a new coordinate, but actually that coordinate is unbelievably simple because, well, z is just itself, right? Like, I don't find z based on this r and theta. That's just a totally separate direction. But this is kind of interesting because it means that cylindrical coordinates aren't much different than rectangular coordinates. When I convert back, again, I'm going to have most of the same stuff. I can see that r squared is automatically going to be given by Pythagorean theorem with x squared plus y squared and the triangle that I have in the picture above. And I know that the tangent of the angle theta could be expressed as y over x, right? Because that'd be the opposite side over the adjacent. And so I know that some theta value could actually make this work. And again, I still know, well, there's no difference in z. Z is always just z. So I can kind of use everything I know from polar, and I can update it to this kind of 3D version of polar in cylindrical coordinates. Our goal, though, is going to be to see how we can do triple integrals and why we would need to do triple integrals using this new type of coordinate system. Okay, so here's at least one important fact that we can go ahead and take a look at before we jump into some examples. Suppose that E is a region. And once I project that region into the xy plane, maybe I've already established like a floor and a ceiling for that region. But when I project it down and I get D, kind of like what we did in the last section, maybe that instead of being like a parabola or a triangular region or something like that, maybe it's really convenient to describe in polar coordinates. Maybe it's like a circle or something like we saw in the polar coordinate section. Then as long as I have a nice continuous function, and as long as E is defined as here's points on the floor, my Z is still bounded from a ceiling to, or from a floor to a ceiling, and as long as D can be described in polar coordinates, then I automatically know that I could easily go ahead and write out things in the following way. I could say this. I could write an integral. My final bounds would be alpha to beta, because those are the bounds on theta. Those would be the numbers. My r might be put up next, and so those would be the bounds that would occur on my r variable. And my innermost variable would be my z, because that's where I'm going to establish that floor and ceiling first. And those are a little bit tricky because these are going to have to be U1 for the floor and U2 for the ceiling, but they can't be the regular U1 and U2 because those are bounded or defined in X's and Y's. So I would kind of have to update those to be described in polar coordinates. And so you'll see how awkward this can look when I write this down. In place of all my X's, I'm going to put R cosine, and in place of all my Y's, I'm going to put R sine. So this looks really big and clunky right now. In fact, it looks so big and clunky that you might be thinking that, gosh, Kyle, I don't want to use this. But I assure you it's not actually that bad. It just looks terrible when we write it down. Now I'm still going to have to write out the function, but again, in place of x, I'm going to put my r cosine theta. In place of y, I'm going to put my r sine theta. But in place of z, I still just get to put z. And then I get to put the order of my differentials. Notice that dz would be first, and then I would normally have had like a dx dy, but we might recall from polar that you can replace the dx dy with an r d theta. And so here I'm going to have an r dz dr d theta. Okay. Again, you can easily move this r around and kind of like permute it with these values at the back, but I always tend to write it in this particular form. Okay. This will be kind of a very, very messy definition that ultimately turns into a very easy process that we can start to employ when we begin to look at several of the examples that are upcoming.